genes. You now, using selection and cut and splice, generate a big, let's say 200 pieces of offspring. Some of them randomly changed by mutation, and then we have altogether 250 possible instances. Now we apply something which is called decimation. We return back to our original count of trials to 50. That is, we have to abandon 200 of those genes. And what we do, we abandon those less fittest. So we calculate a fitness function. We sort the total population by fitness function, and those less fittest go away. And now after this decimation, we repeat the process again. So we go to selection, cut and splice, mutation, decimation, and the whole set of those 4 operations is called epoch. No, well, okay, so it runs and runs and runs. It takes some computer time, and by the time you might get better solution to the problem. Now, what I have shown you is a very primitive genetic optimization. In fact, it is also a little bit similar to the old method, because it explores the space very much by quite randomly at the beginning, selecting new instances. Well, in order to improve the convergence of this method, a lot of things have been done. First, it is important to improve the selection. Random selection is possible, but is it that what happens in the nature? So the second possibility was that only the fittest, the best parents have been selected to produce offspring. Thus, then, on the other hand, it has speeded up the convergence a lot. But if you have one solution that falls somewhere close to a local minimum or local optimum, you would for sure get only this optimum. So yes, it has improved the convergence, but not finding a global optimum. So other methods have been found, and what, for example, one of the methods is called a tournament selection. The other solutions, for example, take the fitness function, and the fittest parents are more probable to create offspring, but the probability is not zero for any of the parents, so that you will be able to get some solutions, and you will not lose the information of somehow good, still imperfect genes that you have collected. So this is the first important point. How do you select those parents to create offspring? Second, surprisingly, cut and splice is quite used in most of the methods. As to mutation, you have several possibilities. You can provide a slight mutation, like changing one bit of the gene, you can do that in a very low number of cases. Or the other possibility is to randomly rewrite the whole selection of bits in many cases. Now this, for more advanced methods, has some inner logic which mostly applies a lot of mutation and heavily mutation at the beginning of the process. And then, as the solution advances to better and better solutions, the number of changed genes and the number of changed bits or alleles is decreasing. So at the beginning there's a lot of mutation in order to find a global optimum, and later the mutation is decreased to improve convergence. As to decimation, there is one more important thing that has a special name, and that is called elitarism. Now, what that does mean? Well, look to the cut and splice method. This is something which is not that works in the nature, by the way. This is something that is very brute. So just remember that if you cut those two genes in some random place, what you mostly get is offspring that is not better than the parents. But yes, you create a lot of offspring and you abandon most of them. But anyway, if you leave the parents, the original set, within the set during decimation, then you set up elitarism to a complete elitarism, because mostly you will not get much different solutions that you already have. The other possibility is that you set elitarism to 0, that is, that you always kill all the parents so that you generate new offspring, but you abandon those parents that have been selected to generate it. Now again, mostly more sophisticated genetic methods do start with low elitarism in order to search the state pairs very much, deeply and randomly. And during the process, elitarism is increasing in order to increase convergence. So those are main ideas of a genetic optimization. Now, that's not a one method. Many people have published many papers, so there are fuzzy methods with some bits that are not clear. For example, there are methods that try to somehow collect good properties that have been already achieved. So, for example, the method is not completely random in selecting the cutting point. For example, it collects blocks of 4 bits that never break. They can be changed by mutation, but they never break by cut and splice. And before I ask you for questions, I will suggest you a special trick that improves the effectiveness of genetic methods when used to engineering problems. I mean, especially for problems that involve real numbers like dimensions, permittivities, densities, and so on. The problem with real number in this simple algorithm using cut and splice is that you easily cut, for example, the exponent from the mantissa of a number, and then you mostly get a completely unuseful solution. Or you could cut the sign, plus or minus, from the number and assign it to a completely different number. So what is mostly done within engineering is, let's say, a process that maps the real numbers to a set of bits, that is not very long. How to do that? Well, let's say that I have, for example, an electric circuit. There is a number of elements, but for each of them I have a minimum value, a maximum value. I mean, for example, I can buy a capacitor which is 1 picofarad. I cannot buy a smaller value. And for, let's say, good dielectrics with low loss factor, I can go up to 10 microfarads, not more. So that we'll have minimum and maximum for capacitor value anyway. And now, within this, I would like to find out the proper value. So I will start with a rough estimation. I will first say, okay, let's assign, for example, 6 bits to this variable. And to do that, I will use a mapping function, 6 bits, that is 2, 4, 8, 16, 32, 64 possible values. So I have this 6 bits, which is, let's say, a number n, from 0 to 63. And I will map this to the real value that is represented by these few bits, like the real value is, well, that's minimum plus n, that's the representation in bits, times the span, which is maximum minus minimum. And now I will continue divided by 64. In this case, I cover the whole span of the variable, but I cover it not very densely. Just imagine we have 60 variables like that. Still, we have 60 times 6, that's 360 bits. So the genetic algorithm should work a little bit around it and find, let's say, an approximate location of the optimum. Once we do that, we change the coding. One of the possibilities is, well, okay, let us increase the number of bits for each variable. So instead of taking 6 bits, we will take 16 bits with 65,000 possible values for each variable. We will now a little bit stretch the gene, and we will repeat the genetic algorithm again with a little bit known result. So with this we will improve the situation, and well, still genetic algorithm could increase the number of bits to represent the real numbers, but what I would suggest at this moment, if the location of the optimum is more or less known, to switch to a gradient-like method, which would work much faster than a genetic one. The strength of genetic methods is the ability to solve problems with huge number of variables. After all, typically those are not, for example, electric circuits, but you may have something like an insert to a coaxial cable, which is more or less rotational symmetric, if I am able to draw it, which has some frequency transfer function. So at some frequencies it's it allows the signal to pass and some not. Now if you want to create this, you would have a number of diameters at different locations, which would be a huge number of numbers or dimensions or variables and an extremely great search space. This you can handle using a genetic-like method, and we have at the moment shown that a genetic method works in some manner. There are two important names. The most known name possibly for genetic optimization was Samuel Goldberg. Who has published a number of works and had a number of PhD students. So in fact let's say the number of works that have been published by this group was very nice, very big, and they have done a lot of work in the area of genetic optimization. And after all, I have to tell that Professor Goldberg was also very wise. First, I have to thank him because when we started our work, he, for example, provided all access to the works of him and his students to us for free. On the other hand, he was quite wise to get money from people. There was, if you wanted to, for example, to talk to him or to get dinner with him, well, he was not free to do that because there was a society for advancement, the work of Professor Goldberg, and this society sold him. So you had to ask the society and pay the society $1,000, and then you can have dinner with the professor. And the society gave the money into research back. So I really enjoyed him, and he has done a big piece of work in promoting optimization. Now, your questions to genetic optimization. Well, if there are no questions, I would like to start with something which could have a genetic optimization as a subset of it, and that's called evolutionary optimization. I will first talk about an evolutionary optimization algorithm itself, and then I will show its application to electric circuits, which possibly could be better understood. But anyway, evolutionary algorithms again start with some estimation of the result, and using evolutionary methods they improve it and find new or better solutions. But in fact, there is no need to have a few population of different solutions. We could have even algorithms with one single instance that evolves. So for example, we have one single instance and we can somehow modify it. And that modification could have two results. First, it improves the fitness function. Second, it does not. Now the first guess would be, let us make only changes that lead to improvement in fitness function. But in fact, this is not mostly a good solution, because of local convergence. If we would like to find a global optimum, we would have possibly to adopt a better strategy, a more wise strategy, which is more or less in that we at one point generate several solutions randomly or pseudo-randomly, and we will accept those new solutions with some probability. Now, the bigger the fitness function is, the bigger the probability is, but it's not zero for any bad solution. Especially at the beginning of optimization, we sometimes accept a solution that is not as good as the previous one, but mostly we accept only better solutions. Now this then can lead into finding a better solution at the end, which is global optimal. Now I will show you this algorithm with application to electric circuits. So far we have been speaking about optimization, which had at the beginning a fixed number of variables. So for example, you had a circuit which had an inductor, a capacitor, and a resistor, and I don't know, and another inductor, and you tried to find optimum values. So you had 4 variables, and you tried to optimize it according to some goals. That was the classic optimization approach. Now we have an evolution of circuit, and in fact we do not know the topology at the beginning. We somehow use an evolution. So for example, in our research we did, after specification of the goals, we specified only one important thing, that is how many ports does the result have. So if we had a filter, it was a 2-port. If we had a frequency duplexer, which sends high frequencies to one output and low frequencies to another output, it was a 3-port, and vice versa. And now we had a universal predecessor of all electric circuits that have been 2 ports. And that was quite a simple predecessor. It was a short from input to output. So it is a 2-port. Unfortunately, it mostly does not follow the goals that we put on it. So how to get from a short to a working circuit? Well, we go there